So welcome back, everyone. I hope you had a wonderful lunch. Our session will start shortly, so please be seated. Our afternoon session is titled Regional Climate Downscaling, Session 1. This session will be chaired by Professor Eun-Soon In and co-chaired by Professor Lu-Ling Xue. So please join me in welcoming our session chairs.
This session, and Dr. Lulin Su will assist me during the Q&A session as a co-chair of this session. We have an exciting lineup of 5 presentations that will explore critical aspects of fine-scale climate simulations. To kick things off, our first talk will be presented by keynote speakers Faye Cruz and Jerasorn Santisirisomboon. So they share some one talk. The first part, for the first part, Faye Cruz will present. So without further ado, let's invite our keynote speaker first.
So good afternoon, everyone. And before I begin, I'd like to thank again Professor Faye Chen and the workshop organizers for the kind invitation to deliver this talk, and which I will be doing jointly with Dr. Jerasorn Santisirisomboon. We are here on behalf of CORDEX Southeast Asia. And so in the first half, I will be presenting some of the current work of CORDEX Southeast Asia. And then Jerasorn will be giving a talk on some of the practical ways in which we deliver this information, climate information for the stakeholders. So I'd also like to acknowledge that this is really not just my work, but also the work of the team. So this shows this timeline shows a summary of the work that has been done by CORDEX Southeast Asia since 2013. And together with support from the Asia Pacific Network for Global Change Research, or APN, and with the fundings from the partner organizations and contributors, we were able to do these activities, which you could see, we could say that it's been done in 3 phases. So for the first phase, which started in 2013, this was a project that was led by Professor Fred Tangang. And at the time, this was in response to the need for climate information because of, at the time, we saw that there was a lack, or at least there's not enough climate impact research assessments for Southeast Asia. And this was due in part to not having access to robust climate information. And so with this project, we were managed to successfully downscale climate projections from the CMIP6 GCMs. And it was about 11 CMIP6 GCMs using about 7 RCMs. And in the next phase, we followed it up by further downscaling this information to 5-kilometer resolution, focusing on the key vulnerable areas. And in this project, this was led by Dr. Jerasorn. The key vulnerable areas that were selected were Peninsular Malaysia, Mindanao Island in the Philippines, the Mekong River Basin, and Java Island. So we are now actually in the 3rd phase of our activities. We're in the first part. We are doing the downscaling of the CMIP6 models over Southeast Asia, and this effort is being coordinated by Dr. Tan Goduk. And we will be using this information for our project, which is the Care for Sea Megacities project that I am leading. And this project, we will be focusing on the Southeast Asian megacities. So we would like to further downscale it to urban scales. So, so for this talk, I will be really focusing on our efforts under this phase 3. So here I'm showing two domains. The first was the CORDEX Southeast Asia domain that we used in the first phase. And we have updated this for the phase 3. And as you can see, there are some slight differences. And this is mainly uh, influenced by learnings from phase 1. So we have extended the domain a bit to the north and also to the west, so that in this new domain, we're able to cover the whole of Myanmar. We would have wanted to also extend the domain to the east so that we are able to capture the tropical cyclones in the western North Pacific, but it was too expensive computationally and data storage wise. So we have decided to have this domain, and I think that this would help us still cover the areas where we want to capture the recurving of the tropical cyclones north of the Philippines. So for these activities, we started off with doing sensitivity tests using the RegCM4 non-hydrostatic model, which is one of the RCMs that we've used, using ERA 5 and running it for about 5 years. And so this was to help us determine an optimal model configuration. When we look at the summary of contributions from the different groups to CORDEX Southeast Asia, we managed to downscale 15 CMIP5 CMIP6 GCMs. And some of these were selected based on Desmet and Goduk, who have ranked the CMIP6 GCMs according to their performance over Southeast Asia. And some were just dependent on the choices of the model contributors, and data availability of the driving conditions were also a factor in the selection. So we now have model output from a suite of RCMs, and the scales range from 8-kilometer resolution. This was coming from the SingV RCM output from the V3 projections of the Center for Climate Research in Singapore. And then we also have 12-kilometer resolution output using HadREM3 from the UK Met Office. And then most of the results that we have are at 25-kilometer resolution using the non-hydrostatic option of RegCM4, RegCM5, and CCAM. For the WRF runs, we are still waiting for this to be added to the ensemble. The scenarios that we have done spans the 4 SSP scenarios that you could see here, where we have also prioritized SSP 1 2.6 and SSP 3.7 as following the CORDEX protocol. So most of the simulations have been done. So we have started the model evaluation, and I will be showing some examples of the analysis. So for example, here we have the seasonal cycle of the temperature from the different models, and it shows the results for the three subregions. One in Indochina, the other is in the maritime continent, and the other is in the Philippines. And we could see that the seasonal cycle of temperatures are well represented, but we still note the cold bias in many of the models, especially when we look into Indochina. As for precipitation, we see a wider spread of the model values, but we could still see that most of the models are able to capture the seasonality. At the Manila Observatory, we have also started to look into the added value in downscaling from these model results. And we could see here the results for temperature, where we find, so this would be the just looking into a 6-member ensemble. So the ensemble will be here, and then the results from the individual models. And we could see that there is more added value over the mountain areas, as indicated by areas shaded in green. And there is still some low added values over areas, especially in the Indochina area. And we think that this is partly due to the cold model bias. For precipitation, we could see that generally there is added value, but we could still see some areas where there is low added value. So that is something that we still need to look into. But what is interesting to also note in these results is the dependence, the seeming dependence of the added value depending on the driving GCMs for the RCM. We are also interested in looking at the changes in temperature and rainfall at different global warming levels. And so here are some examples of the temperature changes at the 2-degree global warming level for the DJF and the JJA seasons. And so what is the key finding here is that we could see relatively stronger changes in Indochina compared to the maritime continent. And we note that there seems to be more like warmer nights in the AJF as opposed to the warmer days in the JJA. For precipitation changes, we could see a wetter wet season. And so this is, we could see that in the increase in rainfall during DJF over the maritime continent, but there is a more pronounced increase in rainfall during the JJA season. And another thing that we'd like to note is the contrasting seasonal changes in extreme rainfall, where we observe more extremely wet days, wet day rainfall in the JJA as opposed to the DJF. So because of these extremes that we anticipate in the future, we wanted to see how that would look like for the Southeast Asian cities. As was discussed this morning, and as we all know, cities are continually expanding with increasing populations. And so we wanted to be able to understand what that would look like, what these extremes would look like for the cities, to give them some information that they can use to for their adaptation planning. And so we are now working on this project, the Care for Sea Megacities project. The long name is actually Climatic Hazard Assessment to Enhance Resilience Against Climate Extremes for Southeast Asian Megacities. So we just use the acronym. And so the objective is to provide and generate the city-scale climate hazard information for Southeast Asia megacities, particularly Bangkok, Hanoi, Jakarta, Kuala Lumpur, and Manila, under multiple SSP scenarios that will be relevant and useful for policymaking to enhance urban resilience in a globally warmer future. So particularly, this project would like to address these research questions. And so one is, how can we develop city-scale climate information for the Southeast Asian megacities, given our limited resources? And the second is, how do we generate climate information that will be useful for policymakers? So yesterday, as was discussed by Jason in his talk, it's really important that the information that we produce are useful and relevant in order to have, so that it can contribute to effective climate action. So key to this project is to increase that engagement with the local stakeholders and the decision makers, so that the information that we produce is useful. So for example, we have invited local stakeholders and policymakers to, even at the beginning of the project. So we had this inception workshop last November 2023 in Bangkok. So that was like 1 month after the beginning of the project. And we invited them so that together we can identify what are the priority hazards for Southeast Asia. And so we have listed here the top 5 hazards for each city. And we could see some differences, but there are also commonalities across the different cities. And so since the common Southeast Asia hazard would be extreme heat and heavy rainfall, this is what we would like to prioritize. On the research side, CORDEX Southeast Asia is also very much interested in building the capacity of the researchers, and in this case, in exploring various downscaling tools for the city scale. And so we have decided to use different techniques and approaches to address the research questions. So for example, for extreme heat, we have these 2 research questions. The first is, how much heat is contributed by land use changes in Southeast Asian cities? And the second is, how will climate change affect extreme heat in Southeast Asian cities? So to address this question, we will plan to use the HRLDAS, which is the High Resolution Land Data Assimilation System, which is an example of a land surface physics-based downscaling technique. And we will be using this model to downscale the simulations at 500 meters for the cities. In the case of heavy rainfall, the research question that we want to address is, how will climate change amplify extreme rainfall events? And so in this case, each of the city will be selecting an extreme rainfall, a past extreme rainfall event that really affected the city. And so the idea would be that this is something that the policymakers would be familiar with and would be concerned about, and to demonstrate how climate change can potentially amplify that extreme event. And so we will be using the urban climate mode of the RCMs, in this case, the WRF Urban and the RegCM5, and to run those models at 1 kilometer resolution for the cities, and to also use the pseudo-global warming method. We are also interested in using empirical statistical downscaling in our project, since most of us are really familiar with dynamical downscaling. So, but this is something that we still need to discuss on how to do it. But initial efforts have been to look into, like, what are the predictors that should be used for example, for downscaling rainfall. Just to mention that this is an ongoing project, so the results are still coming in, but I'd just like to give an example of some initial results. So in the case of extreme heat, this is addressing the question of how much heat is contributed by land use changes in Southeast Asian cities. And so we plan to do these two experiments where they would have the same boundary conditions, era 5, from 2001 to 2020, but they just differ with the land cover land use that will be used. So one will be representative of the year 2001, and the other would be representative of 2020. And so this would mean that we will need to prepare the land cover and land use data set. And so here we plan to use the satellite images from Landsat 7, ideally with low cloud cover, else we would be using cloud removal techniques. Because as you know, in the tropics, we have a lot of cloud cover, so that will be a bit of a challenge that we have to address. And we plan to use this methodology following de Misere et al. 2023, which includes the use of random forest classification, semi-automatic classification, mosaics, especially if satellite images are not able to cover the whole domain, and the use of training samples and image verifications using Google Images, as well as consultation with our local project partners. So to give an example of what that looks like, so we have here the local climate zones in Metro Manila for 2001 on the left and 2020 on the right. And we could see that there are changes that, in the city. So for example, there has been an increase in compact mid-rise, large low-rise, and heavy industry. And we also see a decrease in the compact low-rise, open low-rise, and sparsely built areas. So how does that translate to its impact on the temperatures? We see that, as expected, areas where it was previously non-urban has become warmer when it has become urbanized. And what was interesting that we found was areas where it used to be compact low-rise, which has been converted now to compact mid-rise, became slightly colder. And our hypothesis is that it's due to the canyon effect, where cooler daytime temperatures could be from the shading, and warmer nighttime temperatures could be due to the heat retention or the increased trapping of solar radiation. As for the climate change impacts on these extreme heat, we would be using the downscale CMIP6 models that we've done. But because of constraints in resources and in time, we will be just selecting a subset of those model outputs for the city scale runs. And to do that selection, we have used these two approaches. One is the ranking system of Desmet and Ngodu, and the other is the benchmarking framework for RCM selection of Nguyen et al. In 2024. And so from these two approaches, we'd like to look at which models we can prioritize. So it would be based on the model skill and also considering model independence. And we're also interested in looking at how what are the projections, the projected changes from these model output. So it's still a work in progress. So I hope to be able to update you on that in the next meeting. But for now, I'll end there and hand over the presentation to Jerasorn. Thank you.
Today I'll give some example that we apply our CORDEX-SEA product. One of the most important objective of our CORDEX-SEA is that we need to have establish a web portal and data centers to disseminate our data set. So back to the year 2018, we launched our SUCCESS, is what we call SUCCESS, Southeast Asia's Regional Climate Change Information System. We went to the KL together and launched this web portal. And within this web portal, we disseminate many data sets. We have a data service. One of the most important things is that we have the ESGF node that disseminate our whole downscaling products. This is the first data node in our regions, and we represent our secret CORDEX Southeast Asia. This website jointly managed and operated by UKM, Manila Observatory, and of course in IUCOR in Thailand. We need disseminate the climate downscaling dataset. So this is the ESGF data node that we disseminate so far. We also developed the data portal so that you don't need to go directly to the ESGF, but you can use this web page to connect to our dataset. Apart from the ESGF node, we encourage our colleagues to conduct more research and disseminate more dataset. For example, in the case of Thailand, we have the climate list map. We follow the IPCC list concept to estimate the list and ranking the list in the case of Thailand. We have followed the IPCC concept is that we have the climate hazard, the combination of climate hazard, exposures, and adaptive capacity and sensitivity to get the climate score. So back to the year 2021, we got a project from our government to establish this kind of list map, what we call the list map version 1. And recently we got the second project from the newly established Department of Climate Change. Many of the staff from the Office of Natural Resource and Environmental Policy and Planning moved to this DCCE, the newly established one. So they asked us to revise the climate list map to the version 2. For the first versions, we don't have more experience in preparing this type of list map. So in that case, we combine the exposures and sensitivity and adaptive capacity as the non-climatic variable. And we found that the larger number of some variable will not dominate the list score. So in the second phase, we modified this. This is the first version of our list map. So the second version, we modified it. So we consider variable under the exposures, sensitivity, and adaptive capacity to get rid of this kind of dominate. And we use the latest downscaling product of CMIP6 from our CORDEX-SEA activities to force and to calculate the list map. The difference between these two versions is that we apply the multiplicative to replace the first versions, because the first version we used the additive model and we found the dominate, as I mentioned earlier. And we used the CMIP6 instead of CMIP5. And we used two scenario RCP, SSP 4.5 and SP5 8.5. And the users, we got the feedback from the user that our first versions are a bit complicated to use. So we designed our second versions to fit for different user levels. So the extreme heat index that we apply in this second versions is listed over there, and the extreme precipitation index and the hazard index that we apply in our second versions. We classified it as the intensity, frequency, and durations, not cover the whole. And we conduct 6 consultations meeting with over 200 experts in our country to give opinion and discussion what kind of data set that we need to assess the list in 6 vulnerable sectors, including water management, agriculture, tourism, public health, human settlement, and natural resources. And this is the example of the variable that we apply for exposure, sensitivity, and adaptive capacity under the agriculture and food security sectors. And we got the left is the exposures, sensitivity, adaptive capacity under the agriculture sectors. And we got the heat hazard, flood hazard, and drought hazard, and the list on the right-hand side. And this is the ongoing project, and we are going to present our final versions at the end of this month. This is really first draft of our list map versions. So this slide shows the interactive list map that fit for the general users. They can select only some selections like sectors, climate hazard, climate risk exposures, and climate change scenario, and the period. But one of the most important thing that we revise in this second version is that this for specialized users, the users can select their own to combine the exposure, sensitivity, adaptive capacity. We plan to have at least up to 3 variables that the user can select for exposures and for sensitivity and adaptive capacity. And we also prepare the interactive climate list map or climate map too. And other data service that we have done so far is that we have the data visualizations to show our product, and we plan to expand it to cover the whole Southeast Asia domain, as well as the this data portal. We work really close with the agriculture department in Thailand, and one of the most important thing is that it's very difficult for them to post-process our NetCDF to fit with this kind of crop model. So we developed this portal so they can select the area that they like to have that kind of DSAT input and put it into DSAT model. So we plan to expand to cover the whole domain too. So that's all my presentation. Doja, thank you. Jose.
Thank you for nice presentation. I know you have many questions, but due to time constraint, I encourage the audience to engage the active discussions during the break time. I'm pretty sure Faye and Jerasorn will be available during the break time. So now we will move to the next talk. Professor Faye Chen will introduce 4-kilometer hydroclimate data set.
Thank you,
Let's
Yi-Chi.
welcome the Faye Chen. Yeah.
Thank you, Yi-Chi, and thank you, Faye and Jerasorn. You set a perfect stage, okay, for my talk. It's about this high-resolution long-term climate data set, we call SEA4C, okay, for the entire Southeast Asian, okay, countries. So this is a large collaborative effort, okay, between the UST climate modeling team and our collaborators, okay, from Southeast Asian, okay, science groups. Many of them are sitting in this room. Okay, so I just like to acknowledge, okay, their contribution to this. So why are we doing it? I like to use this slide, okay, from Faye, which make a statement which highlight, okay, the big challenge that despite the increasing climate risk in Southeast Asian countries, we still don't have a very high resolution climate data set that help the society, okay, to assess, okay, and also the climate risk and to enhance the climate resilience, because we don't have the data at the temporal and the spatial scales that are relevant and meaningful, okay, for the state stakeholders. So Faye also summarized this, okay, in her talk. So in the Southeast Asian country under the CORDEX, okay, SEA effort, there are a lot of downscaling data set, okay, developed, but they are coarse resolution, okay, mostly 25 kilometer, but they still produce 5-kilometer scale, okay, downscaling, but only for a limited area. But also this is for the future, okay, climate rejection. So we try to, okay, provide a supplementary, okay, data set, okay, to all this existing effort in terms of the kilometer scale, long-term, okay, historical reanalysis and the future projection, okay, for the entire SEA region. So why we are going to 1 kilometer resolution? It's well documented. This is just one example, okay, for verifying, okay, the precipitation extreme, okay, over the North America, okay, documented in these people. So the best reanalysis data set is YI5. Okay, now people have a lot about this data set. Okay, with very coarse, well, not very, but with coarse resolution 25 kilometer, it's hopeless, okay, to capture the extreme precipitation. Okay, by contrast, the CONUS 4 kilometer resolution, okay, will reproduce the observed precipitation extreme, okay, over all the US regions. So it's very important, okay, to have a convection permitting, okay, simulations to capture this kilometer scale stuff. So inspired, okay, by this, a lot of kilometer scale climate downscaling effort. So we essentially take the same configuration as we did, okay, for the US 404 project, but with a few very important improvement to it that I will mention in a minute. Okay, so this is our Southeast Asian domain. Okay, we decided after we discussed with our collaborators last year, but now they expanded the domain. Okay, so we will stick with this for now. Okay, and probably later on to expand it. But anyway, so the goal, the overarching goal of this project is provide 4 kilometer graded, okay, dynamically consistent reanalysis and the future projections, okay, of hydroclimate conditions, okay. So we have secured the sufficient CPUs and data storage, okay, for this project, and which is a part of the Hong Kong UST, which is the largest, okay, liquid immersion cooling technology. We look at it, how cool. Okay, it really looks cool, okay, to me. So so far so good. Okay, we have in the last months or so, we have complete. Okay, we started from 1969, completed almost 6 years. Okay, yesterday. So roughly, okay, 13% of the entire project. So with this, I mean, the model runs very smooth, no issues. With this speed, we expect, okay, to finish the 50-year reanalysis, okay, by October next year. Okay, so I'm going to show some example, okay, of this. Okay, so we take this data, look at the historical tropical cyclones, okay, in the 1970s, okay. On the left is 1971, okay, 25 tropical cyclones and 18 cyclones in 1973. Okay, so the model, okay, reproduce, okay, this thesis very well. Remember, okay, this is before the global observation network. This is before satellite. So this provide very valuable data set, okay, for the people to look at in the past what happens. Okay, and this is a simulation we did for the Mancot, okay, tropical cyclone that landed in Hong Kong. Okay, so it's past Philippines, weakened, okay, when it landed in Philippines, but also re-intensified, okay, over the South China Sea, and then eventually landed in Hong Kong, caused the huge damage. This is the largest insurance claim, okay, in the Hong Kong, okay, history. Huge, okay, but look at this, how beautiful it is. It's just amazing, right? I mean, it's textbook-like, okay, hurricane, okay, with ice, okay, outer rim bands and all this stuff. You cannot ask better, okay, for that. So we are very excited about this. Okay, since we talk about the kilometer, okay, resolution, the model, okay, resolve the city to some degree. You have to pay attention to the cities. So in this data set, okay, we tested, okay, two urban canopy model, a single layer urban canopy model and the multi-layer, okay, UCM with the building energy model. So we decided, after look at the results, we decided to use the multi-layer, okay, urban canopy model, which produce better results, okay, for cities. So, but not only, okay, the models, but you need to know where are the cities, right? So in the previous talk and yesterday's talk, people mentioned the local climate zone data set. That's what we did, okay. Implement, okay, this global LCZ data set, okay, in the Wolf urban, which has 10 categories, okay, to represent the land use, okay, in the cities, which is pretty decent, okay, in terms of a classification. Not as detailed as we wanted, but it's a good start. So this is the comparison, okay, of the default single generic urban class, okay, in the model, and then there's 11 or 10 LCZ classes. Okay, so on the left is the default land use land cover map. You really need to look very hard, okay, to find these cities, okay, in the Pearl River Delta region, okay. But with the new data set, so that's what it should up. Oh, sorry, going back, okay. So with the new LCZ global data set, many cities, okay, show up. More cities shows up, okay. This is the one example, okay, overall in Thailand, okay. So the default, okay, some degree captures, okay, Bangkok, okay, very small, okay, urban area, okay, but this is the LCD data set, okay, and the big difference is not only, over the Bangkok metro area, but this Pattaya city is completely absent, okay, in the generic data set. So I asked my friend, okay, Jerasorn, okay, he said, this is more realistic. Since he lives in Bangkok, I trust him, okay. So not only, okay, we improve the data set, but also we improve physics. That's more important. Okay. So this blue line, this is comparison, okay, of WRF simulated 2-meter temperature, okay, over the urban sites. We have roughly 1,600 sites, okay, over the Pearl River data region. So the blue line, okay, is this 10-meter surface wind speed, okay. As we know, okay, this is an overestimation of the wind speed that are sometimes, okay, double, okay, the observed wind speed. This is a well-known problem, long outstanding problem, and we have 2 students, very talented. Okay, so they play with the model and find a way. Okay, this new formulation drug, okay, formulation, okay, in the urban canopy model, implemented, and the last shows. Okay, so the new results is showing here in the yellow orange lines, which is much closer, okay, to the observations. So not only 5 minutes, wow, that's too much. But anyway, thank you. So I can finish that certainly by time. Okay, so all this, I mean, so the message is really, we need to, okay, improve models, both the models and the data, okay, in order to improve our simulation, okay, results. So this is a test case for the 2021 extreme precipitation in Malaysia. Left is a WRF, right is the emerge, okay, data set. It's roughly 10 kilometer resolution. Okay, for the large scale, okay, the pattern, spatial pattern, very similar, okay. But the WRF, okay, produce a very detailed, okay, MCS, okay, metascale convection system, okay, in Malaysia, which is we don't see this, okay, in the satellite image. We don't know which is right, okay, because we don't have enough, okay, surface stations to verify that. However, we look at the precipitation difference for the banquet, okay, precipitation, okay, using very different satellite data set, okay, Chen, Persian, CMOF, emerge, okay, different resolution, different data set, okay, different way to retrieve precipitation from the satellite. We compare them with roughly how many stations? Help me. Or 1,000, okay, stations. So when you look at this, it's all over the board, right? The difference, okay, between the satellite, among satellite, between satellite and the observations. But we have statistics, okay. So if you look at the difference, okay, between satellite product, this is wrong. By some reason, it's cut off the bottom. Oh, anyway. So the bottom, most important thing is the bottom line is the SEA4C data set. That doesn't help the microphone. I'm talking about that. Okay. But anyway, to the bottom it shows, believe me, okay. Now I don't have the numbers up on the screen. Okay, so the bottom line shows the difference between the SEA4C and the observation. So the top one is the 4, okay, different satellite. So now trust me. Okay, the SEA4C, okay, produce, okay, the precipitation simulation, okay, not bad, probably better, okay, than the observations, okay, the satellite observations. So this is the point Andy, okay, mentioned yesterday. So thank you very much. I'm done with this. Okay, so we, in the process of producing this 50-year reanalysis data set, which is quite unique, okay, among the the CORDEX-SEA effort, and we are on the way, okay, to produce the future climate projection up to 2060. Thank you very much for your attention.
Thank you. Yeah. Now I would like to invite the audience for one short question or comment. If you raise your hands. Please. Yeah.
Thank you, Faye. This is fantastic. You used the same setup as the CONUS 404. Did you change anything, or were things working out of the box?
Very, very important question, because when we did the CONUS 404, okay, together, we nudge, okay, the 4 kilometer simulation to EI5, okay, but we nudge to a large, okay, wavelength, right, i.e. the synoptic 1,000 kilometer scale, okay, synoptic system, but that doesn't work, okay, for us in the tropical region because of the TC. The tropical cyclone happens with much smaller scale. So when you enlarge, okay, into more wavelengths. So I think in the CONUS 404 we use probably 4 or 5 wavelengths, right? Wavelengths, and here we use 8 to 9. So increase that, and we also increase the weighting factor. I mean, some weighting coefficients, okay, in the spectrology. So that's one of the probably the major thing we did, okay, in the tropical regions. Of course, the urban model improvement, some of the improvement in the PBL schemes, but that's minor. All right.
Okay, thank you. Yeah. Due to time limitation, let's move on to the next presentation. So I would like to invite Laura. Here you are. So she will present less frequent but more intense summertime precipitation in Finland.
Okay, hi everyone. I'm Laura from Finland, Finnish Meteorological Institute. I'm a PhD student, so super nice opportunity to present my recent publication here. And it's the less frequent but more intense summertime precipitation in Finland, and results, of course, from convection-permitting climate model. Okay, now I know. Makes sense. Okay, so the study objective was to provide scientific information for national needs about the precipitation in the future. And when I was sending the abstract here, it was easy because convection permitting model results, but then I was also thinking about the theme, extreme precipitation in coastal cities. And luckily in Finland, most of the cities are in coastal area in the south, where we have most of the precipitation. And then the extreme precipitation. Well, in Finland, extreme is considered to be 20 millimeters per hour. The highest ever measured is 59 millimeters per hour. And yesterday here, I experienced exceeding 70 millimeters per hour precipitation. So that was quite a humbling experience. Of course, the key challenge here is that in Finland, which is a very Arctic country, we haven't really adapted to more precipitation. But however, we have seen more intense precipitation event happening, and that's the problem. Because ecosystem and the infrastructure is not adapted for that. In Finland, we can easily survive minus 40 degrees, 2 weeks, snowfall, easy, no problem. But when it's raining 30 millimeters per hour, there is flooding, there's metros shut down for 2 weeks or so on. So we have lots of learn to hear. And that's why that was the biggest motivation also to start to do this study, because there was a gap. About the maps, the study consisted summertime. So here we see the temperature distribution, and the mean is 12 degrees in the summertime. And of course, and then we see the correlation with the wet hour precipitation with the south-north gradient there. And about the study, introduction, so we used HKUST harmonic climate model that yesterday Ole nicely introduced us. And the simulation data is from the NorCP project. So basically here in the picture, we use 2 different global models and Reanalysis, double nested until 3 kilometer to non-hydrostatic physics. We analyzed the future periods in the middle century and in the late century with 2 different scenarios. So the study itself, it consisted of two parts. So the first was, of course, evaluation of the model data and the observations. And we used like station data, radar data, and analyze it with lots of different metrics. In other studies, we have already seen or shown the added value in this non-hydrostatic physics compared to the lower resolution or the hydrostatic physics, but still we are seeing underestimation slightly in the summertime precipitation in Finland. However, we continue to the second part of the study, the projected changes in the precipitation. First, monthly precipitation, we see a quite noisy signal or not signal at all, and we can't really say too much about this, but this is luckily in agreement with the CMIP6 results in Finland. So nothing to say about there. But then the interesting part that we were able now to study with the convection permitting scales, what was this wet hour precipitation intensity. And here we can see now an agreement in all the simulations that we analyzed. So in the maps, there should be blue indicating decrease and red indicating increase, and there's no blue. So in within the whole country, there's increase in the wet hour precipitation intensity, and the magnitude depends on the simulation scenario or mid-century, late century. And from this, we started to think about, okay, what is causing this increase? Is it like more frequent precipitation events or more intense? What's happening? So actually, we were able to see or show that actually the wet hours in the simulations all showed decreasing trend. So the proportion of wet hours to the total hours were decreasing. However, then we also analyzed, we saw that the frequency of these higher intensities in Finland, considered very high, are showing increasing trend, and the magnitude of this change becomes stronger when we are looking to more higher intensity events. And this also happens in the expense of the light precipitation events. In the study also, we studied more in detail about not only the frequency of different precipitation events, but also the change in the magnitude of these percentile 95 and 99th, and seeing again increasing trend. So not only the frequency of these heavy precipitation events are happening in Finland, or projected happen to Finland, but also their magnitude seem to increase. Then a couple of interesting thresholds I was studying in the paper. 7 millimeters, which is defined as a heavy rain, and then the first threshold for warning, yellow warning in Finland, 20 millimeters per hour. These both thresholds show increase in the contribution in total wet hours. So we are seeing more of these thresholds that are considered to be quite rare in Finland. What is the time? Am I super fast? Okay. Okay, well, I was very fast, so now I can tell you the presentation again in the summary. So in the summary, the objective was to provide the information for national needs that convection permitting model was a very good tool. We didn't really have this kind of assessment before, because this NorCP project is the first convection permitting simulations in Nordic countries. And the need was really there because we are struggling with heavy precipitation events in the urban areas and also in the rural areas. Evaluation showed quite good agreement with the harmonic climate, a little bit cold biased, and underestimating in summer heavy rain. The projections, it's the consistent signal across all the simulation about the increase in the wet hour intensity and then decrease in the number of wet hours. So we are gonna have longer dry periods or at least more non-wet hours. The intensity shifts in this distribution is showing that we are getting more frequently these moderate and heavy events, fewer light events. And then these heavy and extreme thresholds contribute more to the total wet hours. And the increase is happening not only in the frequency, but also in the magnitude. And this was the goal, to provide the information to the stakeholders, policymakers, but also my personal goal was to get the media attention. Like when we are doing science, sometimes it's forgotten. No one is really kind of like getting the information. And that was something that I didn't want to happen. And luckily, with the help of the media department in our institute, I was interviewed in the national news in television last Friday about the results, which was a great opportunity to finally put the message out there. And when we are providing this information, as scientists, we know that there is uncertainty, there is a limitation of these results. Nothing is yet perfect, or might never be. And this needs to be also informed. And maybe adding the kind of like the statement that there is still need for more research and more study for this topic in Finland, but also all over the world. And for future, I have quickly put some lists that I'm interested in to look at or thinking about to look at. And maybe here I would like to highlight the snowfall. So yesterday we listened to a presentation about snowfall in Japan, which is also very interesting in Finland as it's an Arctic country. However, the model that I'm using, Harmonic Climate, is not yet managed to couple with the ocean model. And sea ice scenarios and good sea ice modeling is kind of like very critical for this to projecting snowfall. Now it's kind of impossible. But we are getting there, I think, with the collaboration with inside HKUST collaboration. Also, pseudo global warming approach is very interesting to see more at. Okay, there is the reference, and I think that was it.
Okay,
Thank you.
Yeah, thank you, Laura. Yeah. So I would like to invite the audience for one short comment or questions if you have. Yeah, please.
Thank you for the talk. I'm wondering, have you looking at the mechanism in driving the frequency changes? Particularly, you mentioned about the increase in the intense extreme rainfall, about less light events. Yeah, what about the mechanism? Yeah, thank you.
Can I still have the slides? So in this study, I specifically did not study the physics behind, but afterwards I getting this question a lot. I was reading some research. And for example, here is one study that is kind of like showing some of the mechanisms that I would be guessing would be one good explanation, though it needs more kind of like research. But while we are getting more heat and more moisture is fitting in the atmosphere, the evaporation rises only like approximately 2% per Kelvin. So it might lengthen the dry period between the events, getting like more time between the precipitation event to really kind of release. And when it actually release or come down, it comes more intense as it had more time to grow and develop.
Okay. Yeah. Thank you. Thank you again. And Now we will move to the next presentation. Unfortunately, next speaker will not join this workshop in person, but we have pre-recorded the presentation. So please play. Yeah, now.
Afternoon, everyone. My name is Sean Lam. I'm the Principal Environmental Officer from the Department of Water and Environmental Regulations in Western Australia. Today, I'm going to give you an overview of our Climate Science Initiative project, Dynamical Downscale CMIP6 GCMs for Western Australia. Western Australia is increasingly affected by the climate change, including drought, storm, floods, and bushfire. CSI will generate climate projections for WA under 3 emission scenarios. They are the SSP-126, SSP-245, and SSP-370. CSI use convection-permitting models to downscale from 20 km to 4 km resolutions. Our focus area is the southwest and the northwest of Western Australia. It is a partnership with the New South Wales Government, NACLIM 2, Murdoch University, and Puxi Supercomputing Centre, and it is entirely funded by the Government of Western Australia. So why do we use convection-permitting models? It's because it resolves convective process explicitly. It can accurately capture the magnitude and spatial distribution of coastal rainfall, which is important for Western Australia for the flood risk assessment. This figure illustrates similar precipitation data from 3 models. On the left-hand side is the global climate model. In the middle is the 20 km downscale model. And on the right-hand side is the 4 km convection-permitting model. The CPM clearly captures more localized and intense rainfall near the southwest coast, demonstrating its improved ability to model precipitation patterns. The 5 selected GCMs to force RCMs were selected consistent to NACLIM 2 modeling methodology, and they are statistically independent. The 5 selected GCMs are Access, UK ESM, Easy Earth, MPI ESM, and NOAA ESM. Our simulations are nested within the Australasia-wide 20 km domain data generated by the New South Wales Government, which has minimized our computational cost and time significantly. And we have 2 RCM configurations which are differed by the PBL scheme. R3 is using MYNN2 while R5 is using ACM2. For the purpose of this talk, we are only focusing on 2 seasons, DJF, which is our summer, and JJA, which is our winter. Firstly, I'm going to talk about the bias evaluation using the Bureau AGCD grid observation for Tmax, Tmean, and rainfall. These figures show the Tmax bias. The stippling on the graph represents where the biases are statistically significant using the Mann-Whitney test. The bias is GCM dependent with notable variation across models and seasons. Cold bias are observed in all models during JJA except Easy Earth. R3 ensemble is more cold biased than R5. Bias is generally within plus or minus 2 degrees across most regions, indicating reasonable model performance. Similar to Tmax, the Tmean bias is GCM dependent with notable variation across models and seasons. Tmean JJA generally shows more warm bias compared to DJF. Easy Earth has the largest JJA warm bias. MPI ESM and UK ESM show cold bias while NOAA ESM and SS show higher spatial variability. For the rainfall bias, a drying trend is observed in both seasons. Most of the models are dry biased during DJF or have small biases. JJA bias is significant and higher. R3 is wet while R5 is dry biased. We are still investigating the difference between the 2 RCM configurations. Having these 2 configurations is a good thing as they can better capture their variability. Then I'll present the time series plot of temperature and rainfall anomalies using 1951 to 1980 as baseline. The shade area represents ensemble range, while the solid line represents the ensemble mean for each SSP scenario. These figures show the seasonal maximum temperature anomalies. Maximum temperature highlight daytime extremes. The Tmax warming by 2100 ranges from 1.3 to 3.7 degrees across all scenarios. Higher temperature anomalies suggest more frequent and intense heat waves. Warm winter in JJA could disrupt ecosystem and agriculture as well as water cycles. These figures show the seasonal minimum temperature anomalies. The T-mean warming by 2100 ranges between 1.3 to 3.4 degrees across all scenarios. Minimum temperature reveal critical nighttime warming trends that are often stronger and more impactful under climate change. There are potential heat wave and health implications under both seasons. Together with Tmax and Tmean, they provide holistic view of potential thermal stress in southwest of Western Australia. For seasonal rainfall anomalies, there's no strong trend towards wetter or dry conditions in summer. However, there are spikes in extreme events that could stress flood infrastructures and agriculture systems. In winter, there is notable downward shift in ensemble means, especially toward late 21st century. The consistent drying trend is getting stronger in the SSP 370. It raises concerns for water supply, reliability, ecosystem health, and bushfire risk during the dry winters. The following slide shows spatial patterns of mean climate change signal for southwest of Western Australia, comparing near future and far future periods against a baseline between 1980 to 2010. The stippling highlights area where at least 70% of ensemble members show significant and consistent change. Climate change signal in Tmax appears significant over the entire domain across timeframes and all scenarios, suggesting it is statistically significant. Warming is stronger in summer than winter, especially under SSP 370. SSP 245 show moderate warming increasingly aligned with SSP 370 by 2100. A clear north-south gradient is observed with stronger warming in the north region. Inland areas also experience more pronounced warming compared to coastal zone. The climate change signal in mean appears significant over the entire domain across all timeframes and all scenarios, suggesting statistical significance similar to Tmax. The increase in Tmean is generally consistent between seasons. However, for JJA under SSP 370, Tmean seems to show a reduced warming signal compared to the warmer seasons. This is not really apparent in the SSP 126. The Tmean climate change signal appears to be impacted by the underlying land use, which is especially apparent along the eastern border of the wheat belt regions. Yet this is yet to be investigated. For the seasonal rainfall climate change signal, a coherent and significant drying trend is evident across central southern regions, with huge implications for water resource and agriculture. The signal is strongest under SSP 370, but even under SSP 126, the persistent drying trend affects key areas like the coastal plain, wine regions, Great Southern, and the wheat belt. The trend remains evident even in the weather bias model like the ECF. I note there are few extreme rainfall events currently happening in Hong Kong. Our CPM model is being applied to the CORDEX flagship project, focusing on modeling short-duration rainfall extremes in Australian cities. For Perth Metropolitan, 4 major events were identified using the Bureau AWS, radar, Barra C2 data, and RCMs initialized accordingly. Climate simulations explore 2-degree versus 4-degree warming scenarios using adjusted SST and atmospheric fields, supported by high-resolution dataset and coordinate urban landscape assumptions. In summary, the model biases are within the expected range, supporting the robustness of our simulation framework. Using multiple RCM configuration enhances our ability to capture internal variability, especially for rainfall. The projected climate signal for Southwest WA align with the established trend, reinforcing the confidence in our result. This work is made possible through the support from the WA government, partnership with New South Wales government, Murdoch University, and the Puxi Supercomputing Centre. Future work include the Northwest WA domain climate data productions, added value assessment, comparison between CMIP5 and CMIP6, GCM RCM comparison, and all of these manuscripts are under development.
Okay.
That's the end of my presentations. And
So, first, let's appreciate his presentation. So, although he's not here, he's waiting for your comments and questions online. So, I would like to invite the audience to ask any questions or comments. Anyone? Yeah, sure.
For online participant, if you are able to use the Slido channel, please leave your comments there too. We encourage also in-person participant, if you are not comfortable asking directly, please pass your comments in.
Any comments or questions? Oh, yes, please. Yeah, he's waiting for.
Thank you very much, Sean. I really like your presentation, especially that can see that what we're going to happen in Australia. My question is, you look at that. You also mentioned about that the land use could be affected with quite a lot. Do you know what you could do? Can look at the land use change and so on more to make sure that in fact your model that can we present the land use reasonably?
Thanks for the questions. Yeah, we are looking at updating the land use in 2 projects. One is the Urban Heat Island project, which downscaled the data further to 1 kilometer using the latest available land use informations. And we also have another project that one of our postdoc is doing is to look at the land use change projection to the future, like how changing the land use will affect the climate. And the application for this project is for agriculture, which is quite a large industry for Western Australia. So yeah, we'll please stay in touch if you want to know about like how the land use change is going to affect the climate for Western Australia. I think there will be some publication coming up in the next couple of years.
Okay, thank you. And any other questions? If not, then Xian, thank you very much for your contribution to this workshop. Yeah, thank you. Yeah.
Thanks.
And now we'll move on to the next presentation by Yi-Chi Wang. So I would like to invite our speaker, and he will present turbulence parameterization scheme of local climate zone-based urban morphologies.
Okay, thank you very much. And I'm Siyu from HKUST, and my supervisor is Jiachun Yang. And today I'm going to talk about the turbulence parameterization scheme of local climate zone-based urban morphologies using large Eddy simulation. So more than half of the global population lives in urban areas, and the turbulence exchanging process between the urban boundary layer has a considerable influence on human activities, such as urban climate and the pollutant dispersion. On the one hand, the flow between the flow within the UCL will be feedback into the UBL between the exchanging process of the momentum and scalar. And on the other hand, the flow pattern within the UCL will still be dominated by the UBL. So the key point is to figure out the exchanging process between UBL and UCL. And large eddy simulation is an increasingly popular method because it can capture more flow details than RAD. So it is more suitable for explaining complex 3D heterogeneous flows. But when using a large eddy simulation, it often faces great challenges because it requires finer grades and more complex setups, and it often faces high risk of error due to the simulation complexity. So general guideline for practice is still needed. Even with the same research objective, the numerical setup in large eddy simulation is still remain diverse, such as the grid resolution, inflow conditions, wall models, and subgrid scale. And the validation strategies also varies a lot because with some study only offer the quantitative or some limited data for the validation. So the validation still makes it difficult to demonstrate the accuracy of the model. So in this work, we would like to explore and propose a more systematic areas configuration, especially for urban climates, including calculation domain, match strategies, and validation strategies. But due to the heterogeneous of the urban airflow, so we will choose two extreme configurations, that is the aligned array and the staggered array. So validation strategies also is very important because LES, it can provide more flow details. So it can provide more physical quantities in terms of the velocities time series. So the validation, if we only use the mean quantities produced by runs, is not sufficient. So we will use the data of the multiple order data for the validation. Then the LS model will be used to different LCZ. So first, we would like to get a fully developed turbulence in the spatial scale. So we will not use the periodic boundary conditions. Instead, we will conduct a full wind tunnel into our numerical simulation. And the distance from the outer building to the inlet boundary will be set to 5H, and the boundary layer thickness will be set to 10H. This two matrix makes our simulation meet the blockage ratio requirements. And there comes another question. The biggest advantage of using a periodic boundary condition is that it can save a lot of grids. If we replicate a whole wind tunnel into our numerical simulation, the total number of grid will reach a number of 3 billion. So even with such advanced resources nowadays, it is also unacceptable. So instead, we will use non-conformal grid strategies. So in the greatest of the core region, and the cube will be discretized by 40 grids. And the grid will be expanding outwards at a doubling range, so that finally the total number of the total grid number will be 9.3 million. And to better compare with AIJ's wind tunnel test, we will use a logarithmic law for linear fitting to obtain the inlet profile. And the vortex method will be used to generate the inflow profile fluctuations. And for the near wall model, we will choose the wall functions. Another point is to get a fully developed turbulence in time scale. But this requires the turbulence to reach a steady state. But what I want to emphasize here is it is not very good for us to describe the turbulence in the world of steady state, because the ever-changing nature of turbulence makes it impossible to get to identical flow. So we can only use the word of statistical stationary to describe the turbulence. So in practice, we will use the data which skipped an initialization period of 125 eddy term time, and the data of 200 eddy term time will be included in our analysis. So by monitoring representative points in the flow field, we can see that the flow field in our simulation has reached a statistical stationary state. Now let's recall the definition of LES. A proper implementation shall resolve all the large scale eddies and only model the smaller and more trivial ones in the energy containing in the dissipation range. That is to say, if an LES filter sits inside the inertial subrange, and the Navier-Stokes equation will guarantee the accuracy of the large eddies. So in practice, the grid resolution is often the most indicative for LES. So the demarcation point between energy containing range and the inertial subrange is by ensuring that 80% of the TKE will be resolved. So by looking at these two figures, we can see that there's only a small portion near the edge where slightly falls below 80%, and in the core region of our greatest interest, it exceeds 90%. And to look for another assurance for our LES, we will use LES IQ for the verification. If LES IQ is less than 80%, it indicates a very large eddy simulation. If LES IQ is larger than 80%, it is a proper LES. And if the LES IQ exceeds 95%, it means a DNS. So by looking at these two figures, we can also confirm that only in this region, in the outer region, the LES IQ is less than 80%. So in the core region of the great interest, and the LES IQ exceeds 95%, it is nearly called a DNS. So by now we have demonstrated the accuracy of our studies. So for the validation, we will use multiple order data. So now for the aligned array, we will use first order data of U standard deviation of UVW and TKE. So from the table, we can see that most of the matrix meets the requirement. Only TKE is slightly below the threshold. And by looking at the scatter plots, we can see there's a strong correlation between LES and our the longitudinal experiments. So for the staggered array, we can see that in the inside the canopy layer and the vicinity of the cube results are all in good requirements with the previous studies. And the development above the cube is still reasonable because it is mainly influenced by the boundary layer circulus. Our boundary layer circulus is 10%, and it is more close to the PIV. So the two key metrics of the first order data for staggered array is the Reynolds shear stress and the standard deviation. By looking at these two figures, we can also confirm the accuracy of our model. Only in these figures, we can see our model is slightly overestimate the standard deviation of the vertical velocity, but it is more closer to the Winton data. These two metrics also validate the accuracy, but the span-wise velocity is often the most challenging to predict. But we can also see that our simulation gets the correct trend of the profile. So now comes the results. By looking at we will look at the vertical turbulent momentum flux. In this figure, we can see there are more red value regions. So we can see that this region means that the airflow goes horizontally and it interacts. So which means that the staggered array will boost the vertical turbulence exchange. But on the right side, in the aligned array, there are more regular regions. So which means the flow goes horizontally and the vertical turbulence exchange is weaker here. So now we will look at the vortex visualization. We will use a Q criterion. Omega is a vorticity tensor, and S is a stream range tensor in the local area. If a positive Q value means that the rotation dominates the string here. So by looking at, so first I would like to guide you to see the picture on the right side. In this side, we can see that the building will form a straight channel, so which will guide the flow to go horizontally, and it will form a streamwise channel vortex. So in the aligned array, the streamwise channel vortex will restrict turbulence to the horizontal pathway. But we can see on the left side, the offset layout will break the channel, so the airflow will go horizontally. So the vertical penetrating vortex in the stacked array will enhance the vertical momentum transport, which are contributing to the stronger and more complex Reynolds stress patterns. So by now this study has proposed an AIS-based turbulence parameterization, which can successfully capture the complex flow details. And we have put forward an validation strategies. Our next step is to make this AIS framework into different LCZs to bridge the gap between the numerical simulation and the real-world application. So that is all my presentation. Thank you.
Okay, thank you, Siyu. So now I would like to invite the audience for questions or comments. Don't be shy. Any comments or questions? Okay. Yeah, please. Yeah.
Thank you.
How do you say you can use this type of idealized LBS situation to improve the urban model?
Yeah. In my understanding, they are more in the single layer model. The vertical profile will not be changed through different urban morphology. So we would like to use this LES frame to different urban morphologies to get a totally different vertical profile of the single layer model to improve the accuracy of the single layer model in our application.
Any other questions? If not, then thank you again. Yeah. So now I would like to conclude this session, and I really appreciate all your contributions as speakers and participation, the audience. And now our MC would like to announce the next arrangement.
Thank you. So now we will take a short coffee break for 30 minutes. Refreshments are available outside the lecture theater. Please return by 4 p.m. For the final session of the day, Regional Climate Downscaling Session 2. Thank you.
Welcome back. Our final session of the day is the Regional Climate Downscaling Session 2, chaired by Professor Seong-Ki Park and co-chaired by Professor Yanping Li. Please join me in welcoming our session chairs to the stage.
Thank you. This is the last session of the day. It was quite a tough day, right? We have 4 presenters. The first one starts from Kristen Rasmussen on the title of Extreme Storms in Current and Future Climate. Please.
Thank you. Well, I'm on day 2 of jet lag, so I'll try to keep everybody awake. I know it's the last session of the day, so thank you. Thank you to the organizers, and I'm happy here to talk about extreme storms in different climate states, particularly from kilometer scale modeling. I have a lot of students, postdocs, former PhD students, including Aaron Doherty here in the audience, to thank for this work. Okay, so if we think about kind of the global implications of weather disasters in the United States, we are seeing that these billion-dollar disasters are becoming more frequent. In particular, in 2023, the US was actually hit by a record number of high-cost disasters. And just recently on July 4th, we had a very devastating flood in Texas that had 135 fatalities that will be talked about for many, many years in terms of the failures of emergency management communications in this catastrophic event. In Asia, we've also seen that these events are also increasing. So this is an example here going through 2012. We would see this probably continue here. And motivated by yesterday's record-breaking event, this is a very real topic that a lot of us globally are very interested in thinking about. Okay. So this is work that Erin Doherty did at the tail end of her PhD, looking at almost 600 flash floods in the United States from convection-permitting simulations, the CONUS-1 simulations. The current rainfall intensity here is shown in the blue, and the future in the pseudo-global warming RCP 8.5 scenario is shown in the red. And we can see that we expect to see future flash flood rainfall becoming more intense relative to the current climate. And these are things that we're seeing, and we're really paying attention to the rates that are changing. Okay, so just like Professor Yu do, I was motivated by the event of yesterday, and I actually changed my talk yesterday to include a little bit of information about how very small changes in some coastal topography impact some heavy rainfall in southern China. And so this was work led by Marong Zhang, a visiting student who worked with me for about 6 months. We did some terrain modification experiments in WRF over this region, looking basically at 2 main simulations. One is a control simulation of this entire region. The second one is a no coastal terrain. So we removed basically the small coastal topography. There was an interesting complementary study that you showed this morning actually on this. And then she ran basically 3 composite heavy rainfall training backbuilding systems over this region, built composite environments, and we ran WRF with these scenarios. And one of the things that I wanted to highlight is we did actually remove topography in the Hong Kong region, so that this is one of the reasons I want to show this here. So we noticed that when we removed just the coastal topography, the small mountains along the coast, we saw a reduction in rainfall by quite a lot. You can see the nice horizontal banding structure that came out from this control simulation, and the precipitation was much reduced with just the absence of the coastal topography. And Marong showed in complementary work to Yu's work that we actually see a reduction in the low-level jet impeding into the continent with the presence of the coastal topography there. Without it, you see that the low-level jet is much stronger. It brings more of that moisture into the continent. But the interesting thing is that we actually have reduced atmospheric moisture transport into the continent basically with the control simulation because of the blocking effect of that topography. And so from this work, she built a nice conceptual model showing that on the left-hand side, when we have our control simulation with the coastal topography, we basically block that incoming low-level jet moisture. We actually initiate convection along that mountain, and the cold pool, like you mentioned as well, helps to actually make those convective cells more stationary and stronger in nature and more long-lived. Whereas without those features, this moves inland. And so the comment here, I did see some exciting work from Faye Chen that they're running some simulations here over this region. It's really important to actually consider the impacts of small-scale coastal topography. 500-meter mountains make a big difference actually in the localization and the organization of these long-lived and very impactful rain bands. Similarly, we actually did some work in Taiwan where we took the full topography on the left. We reduced the topography by 50% on the right-hand side. For the 2017 Meiyu front, this was also another record-breaking event in this region. And similar to what we saw here, when we make large mountain changes, we also see a very important reduction in the orographic precipitation over the mountains. And so I'll comment here that it's also important to consider the impacts of large coastal topography in future climate simulations as well. Okay, so now I'm going to scope out a little bit broader to think about a question: how may storms, or how will storms change in the future climate? This is a graphic that was built from a previous paper that I'll go through here with the motivation of really looking at the extremes in a future climate state. So what we did is we looked at the CONUS-1 simulations. We looked at different ranges of reflectivity from very weak on the very top left, 0 to 10 dBz, and this is the difference between a pseudo-global warming climate. We subtract off the control climate, and the differences are shown here in the colors. What you'll see is anywhere there's blue, we're seeing reductions in the frequency of these events. As we scope into the higher ranges, the stronger systems, we actually see this change more to red. So we're seeing fewer weak to moderate systems and more increases in the strong storms in the future climate state. We can represent this here. The reflectivity ranges are on the x-axis, and the difference in percentage from the control is on the y, showing anywhere below that dashed line, it's reductions, anywhere above this, it's increases. And we see that there is a reduction of the low to moderate frequency intensity storms, we see increased frequency of strong storms, and this indicates a shift in the population. This is not just everything becoming more intense or more frequent. We are seeing that there's a shift in the population with these CPCM simulations. We also then wanted to look more into the mechanisms. Why is this the case? Why are we seeing more extremes in the future? And so we looked at the thermodynamic state motivated by work looking at broad scale frequencies of convective storms on a global scale. This is work that I did with my advisor Bob Howes, looking at basically where different modes of convection occur on a global scale. One of the things we learned from the TRMM satellite is that among the most intense storms on Earth occur near the largest mountain ranges. The reason is because these regions have a combination of both low-level moisture coming into a region and then also some sort of a capping inversion, a dry layer or a warm stable layer to basically allow for that instability to build up over time. So we looked at these environments in both global climate models and CPCM models and found that basically convective available potential energy, the energy available for convection to tap into, increases everywhere in a future climate. The difference is shown in the bottom panel here, with everywhere basically being red, particularly east of the Rockies. We then also looked at the negative buoyancy, the convective inhibition, basically suppressing, or you have to overcome this negative buoyancy in order to realize your potential energy. And we found that the magnitude of this negative energy actually increased as well in magnitude. So there's more more negative buoyancy to overcome, but if you can overcome it, there's more potential energy to tap into. We've also looked at this on really large scales. Here's an example of area interim reanalysis on the top and CCSM4 GCM 6 hourly data on the bottom, for CAPE on the left, SIN on the right-hand side. And we see that broadly, these GCMs are actually capturing the thermodynamic patterns of these variables quite nicely. We also can zoom into this, looking at the differences in that same CONUS data. We see very complementary patterns from the kilometer scale models on the top and the GCM data on the bottom. So motivated by this, my group has now thought about what we can do with this representation. We're representing the thermodynamic environments supporting these systems relatively well. What can we do with this? And so we are taking the environmental conditions that we know lead to the occurrences of convection, and we're actually combining these into to try to use a machine learning algorithm to predict the frequency of convection at the kilometer scale modeling framework. So to do this, we're basically taking 16 features, environmental variables, here including water vapor, there's CAPE, there's LCL in here, and we're trying to predict the frequency of convection. We did a stratiform convective separation. We're trying to predict the occurrence of convection in the CONUS 404 data set. We're training from 2018 to 2021. We actually coarsen out this CPCM data to 28 kilometers because there's a lot of data. We also randomly removed 90% of grid points. I can talk about the details. We did a lot of testing. It didn't actually matter which percentage of randomly removed points that we used. And we're using a multi-layer perceptron for this particular example. And so here's the result. So CONUS 404 on the top, this is the convective frequency over 40 years in the current climate. The middle panel shows the MLP predicted convection frequency, and the bottom is the difference. And so what you can see here is there's actually very few differences. This modeling system is able to capture a lot of the variability, a lot of the occurrences of the convective systems in this CONUS 404 framework. We also compared this to a very, very simple linear regression. We don't expect this to perform well, but you can see basically that relative to linear regression in blue, the MLP system is doing quite well relative to the ground truth. We also looked at this with respect to the diurnal cycle. One of the drawbacks, one of the challenges of global modeling is that GCMs often represent the opposite diurnal cycle. For example, over the United States, they often have a maximum in precipitation at noon local time, which is not what we see. We actually see a nocturnal max. We're actually seeing with the MLP system in green that it is capturing kind of the afternoon diurnal cycle of convection, which we do expect to see over our region. And you can see the ground truth there in blue. Finally, we did look at a case study. So this is a case study on the left-hand side. This is actually from the CONUS 404 The blue data is the 4-kilometer high-resolution version of where the convective frequency is. The red is the 28-kilometer coarsened version of that, so you can see that they lie right on top of each other. This is the MLP prediction, so it's a little smoother. It's not as high resolution as the one on the left-hand side, of course, but it gets the right positioning and the kind of the locations of these convective systems quite well, indicating that the environments that these storms are forming in are being well captured by this MLP trained system. Okay, so I would just end here thinking about the exciting opportunities actually for machine learning and CPCM. This is likely because of a very high fidelity representation of mountain processes, diurnal cycle, storm dynamics. These are really important processes to capture that can help us understand the connections of environmental conditions to these systems in a variety of modeling frameworks. So in conclusion, we saw that both small and large scale coastal mountains are really important in representing heavy rainfall in China and Taiwan. We did look at convective populations, showing fewer weak to moderate systems and more extreme storms in a future climate. This is a shift in the convective population that is likely explained by increases in CAPE and also increases in SIN. And this is consistent across models in all scales, including CPCMs and GCMs. We then also see that machine learning algorithms have some exciting opportunities for kilometer scale modeling, particularly because of the high fidelity of the processes that we can represent at high resolution. And I would like to say that this provides really interesting opportunities for these models to enhance our understanding of the future of extreme weather. So with that, I'll stop and take questions. Thank you.
Thank you. Any question or comment?
If there's time.
Okay, Xiaoming.
So thanks for the fantastic talk. So I have a question about the machine learning part. I wonder if you get a chance to train the machine learning model with historical data only and then test its performance for future.
We have, and the performance is actually really good. It looks like actually the system learns the relationships between the environmental parameters that we give it and the occurrences of convection. When we point that current model trained on the CONUS 4.4 in the current climate to the future climate, it does a pretty good job of actually reproducing the convective frequency in a warmer state. It was pretty surprising, but we did do that testing. I didn't have time to show it, but I can show you that offline if you want.
Okay, yeah, that's encouraging results.
Yeah, it's very exciting actually. Yeah, thank you.
Okay. Okay, yeah, you.
Yeah, very interesting talk. So my question also relates to the machine learning, and notice that your model can generally capture the diurnal cycle, but the peak seems later. Do you have any explanation about this shift?
That's a great question. We're looking into that right now. And actually my postdoc Hung Rei is doing some ablation studies where we actually train on a particular part of the domain and exclude other parts. And we're doing testing to see why the shifting of the diurnal cycle is off. But yeah, I'll have to report on that next time. But we've noticed that as well, and we're doing some ablation studies to test that question.
Okay, thank you.
Yeah, thank you.
Okay, thank you, Kristen. We'll move on to the next one. It's by Yi-Chi Wang, assessing the impact of cumulus convection and turbulence parameterizations on typhoon precipitation forecast.
Okay, hello everyone. I'm Wang Yueya from the Hong Kong University of Science and Technology, and I'm glad to be here to share our work about assessing the impact of cumulus convection and turbulence parameterizations on typhoon precipitation forecast. Sorry. Yeah, it works now. Thank you. So the typhoon, it attacks South China and caused extreme precipitation events almost every year. But the forecast skills of such extreme precipitation events actually is also very limited, as shown in this right figure. So we can see the x-axis and y-axis represent the success ratio and POD index for different precipitation threshold. So we can see the extreme precipitation, which over 50 millimeter precipitation forecast actually is get very low precipitation scales even in the most advanced observational centers. So the factors affect such extreme precipitation events forecast is very complex, like the large-scale circulation and the topographic description and the dynamical process in the numerical models. But one of the most challenging and important reasons is associated with the subgrid scale process description in the numerical models. So the previous studies, they suggested like we should turn off the cumulus parameterization when the resolution reaches to 4 kilometers. But whether we should turn on or turn off such cumulus parameterization actually is also very debating. The other point is even the PBL scheme, it is still valid in the kilometer scale, but the conventional PBL scheme, it doesn't consider the subgrid scale effect in the horizontal direction. But the previous observation and simulation experiments, they point out like the temperature gradient in the horizontal direction actually is also very important for the storm or the typhoon precipitation forecast. So here we proposed a new turbulence scheme, which is named as RNA scheme. It can consider the backscatter effect in the horizontal direction. So this is the functions we use to represent the turbulence effect. I will not go into details about these functions, but here I would like to highlight the second order terms in the functions. It can account for the backscatter and normal stress in our RNA scheme. So after integrating this new RNA scheme into the WRF model, we conducted a set of experiments as listed in Table 1 to for several typhoon cases. For example, this GFGFR simulation, it means we combine the Gariel filters cumulus scheme and the new RNA scheme in the simulation. So we have several typhoon cases to test the performance of the new RNA scheme. But here, I use the Typhoon Mujige and Typhoon Hato as the example cases to show the performance of the RNA scheme and also the combination of different cumulus schemes. So because we mainly focus on the impact of the new RNA scheme on the precipitation forecast, so first we evaluate the precipitation as shown in this left figure. In the first row, it shows the average precipitation for different simulations. So we can see after applying the new RNA scheme, actually it produces more precipitation compared to other simulations. But whether this more precipitation is real or it is false alarm, we further calculate the recourse scores and also the precision scores to evaluate the ability to catch the extreme precipitation events. So here I would like to mention the recourse scores. Actually, it measures the ability to catch the extreme precipitation events, and the precision, it measures the number of situations which can correctly predict it in the simulation. So first, for the recourse scores, let's focus on the Typhoon Mujige case. We can see if we apply the new turbulence RNA scheme, so in the which is represented by the purple and blue dots, it shows higher recourse score compared to other simulations. But if we further combine the new RNA scheme with the Gariel filters cumulus scheme, it shows even higher recourse scores, which means applying this RNA scheme, it can produce higher recourse score, but if we both applying the cumulus and new RNA turbulence scheme, it can further improve the ability to catch the extreme precipitation events. But we also notice, like, if we apply these two cumulus and RNA schemes, at some cases, it may have lower precision scores, which means the RNA scheme, it can sometimes overestimate the precipitation and showing lower precision scores. So we further calculate the relative error between the observational results and the observation and our simulation results. We plotted these violin figures to show the relative error results. So this is quite complex. So let's first focus on one case, which is for the Typhoon Hato and for the precipitation over 120 millimeters. So this green violin, it represents the simulation which applied the GRIL 3 cumulative scheme and also the RNA scheme. And we can see it shows lower relative error compared to all the other simulations. And we also find like the shape of the relative error actually is quite different among these simulations. For the simulation applied both the cumulus and RNA scheme, it generates the stations which shows lower relative error actually is more than other simulations. So the other thing I would like to highlight is the performance of the two different cumulus schemes actually is also different. First, if we focus on the Typhoon Mujige, we can find if we combine the GRIL freighters cumulative scheme with the RNA scheme, actually it shows lower relative error compared to the GRIL 3 cumulative scheme. But for the Typhoon Hato case, it actually shows opposite results. Here, we believe it is because the GRIL freighters scheme, it is a skew-aware scheme, which means it is not that sensitive to the resolution. But the GRIL 3 scheme, it is more sensitive, so it generates more intense precipitation. So in the Hato case, the typhoon, the precipitation generated by the typhoon is more intense. So the GRIL 3, it shows a lower relative error compared to the simulation used the GRIL freighters scheme. So after evaluating the performance on the precipitation, we further examine the new RNA scheme's effect on the typhoon structure. This is one snapshot of the Typhoon Hato, and this is of the observation, and this is of the simulation results. We can see there's no intense convection over the Hainan Island. But if we didn't apply any cumulus RNA scheme, actually it shows intense over the Hainan Island. And after applying the RNA scheme and the GRIL 3 cumulus scheme, the false alarm actually is removed very well. And also, the typhoon structure is more compact in this simulation with new RNA scheme. So we further plotted the radial wind to further examine the effect on the typhoon. So we find after applying the cumulus and RNA scheme in this left top figure, we can see it significantly generate larger radius of maximum wind as shown here, and also a deep radial inflow, which means it also generates strong radial wind by applying the RNA scheme. So in conclusion here, by applying the array and cumulus scheme, actually the simulations can generate more intense precipitation. So we further calculate the mixing of the horizontal momentum and potential temperature to give them dynamic analysis for the improved performance. So this is the functions for calculating the mixing version of the mixing of the horizontal momentum and other and also vertical velocity and potential temperature. So first, if we focus on the horizontal momentum, we can see this negative value, which means upgradient mixing. It shows upgradient under below the 2 kilometers, which is associated with the increased tensile wind as we showed before. And we think it will further invigorate the convection through the secondary circulation. And also, we see the optimal configuration for the potential temperature. And we see the downgradient mixing of potential temperature at a low level, and I think it will enhance buoyancy and further induce more vigorous convection during the simulation. So here's our summary. So in this study, we proposed a new turbulence scheme, which is named as RA scheme. It can consider the turbulence effect in the horizontal direction. And after we conducted the different simulations by combining different cumulus and ion scheme, we find by using these two schemes, it can improve the ability to catch the intense precipitation events. And also, this is due to the optimal configuration of the dissipation and backscatter configuration. And also, we point out like the cumulus scheme actually shows different results. It depends on typhoon cases. That's on my presentation, and I will stop here and welcome any comments and questions. Thank you.
Okay, questions or comments? Okay, Andy.
Yeah, thank you very much. Are you planning to test the new PBL scheme in other situations as well, like MCSs, or more like as a weather forecasting, where you see that if this would make sense as a general setting involved?
Yeah, I think that is our future work, because I think this backscatter should be also important for other convection development, like the warm sector cases or other extreme precipitation cases. Yeah.
Any other questions? So your inner domain was the resolution was how much?
The inner resolution is 1.67. Yeah. Yeah.
So usually we do not use convection parameterization in that case, right? But your result shows that using convective parameterization is better than no convection parameterization.
We actually we use the cumulus parameterization in some simulations, but we also have a comparison simulation which didn't apply any cumulus scheme. In our case, by applying the cumulus scheme, even in the 1.63 resolution, it can impress the ability to catch the extreme precipitation events. Yeah.
Okay.
Yeah.
Good. Another comment? Question? Okay. Thank you. We'll move on to the next one. Okay, Puxi Li. Convection permitting simulation of extreme MCS over the Tibetan Plateau and its downstream. Please.
Thank you, Chair. Good afternoon, everyone. My name is Puxi Li from the Chinese Academy of Meteorological Science. Today, I want to share our recent work focusing on the convection-permitting simulations of mesoscale convective systems over the eastern China, which is downstream of the Tibetan Plateau. And this is also the insights from the first example run of water year 2020 in CORDEX flagship pilot study, convection-permitting over the third pole. I want to give my thanks to all the modeling members in our project first. And here is my outline. As we all know, the MCS are large, organized, deep precipitating convective storms that extend hundreds of kilometers and last for several hours. And they often occur in the tropical regions and area downstream of huge mountains. And they frequently generate high-impact weather events, such as heavy precipitation, flooding, and hail and gusty winds. So in terms of the kilometer scale convection-permitting modeling, we all know that the convection-permitting modeling shut down the deep convection scheme, which are widely known as the largest uncertainties in precipitation simulations. The convection-permitting models offers a path towards fundamental advances in our understanding of key factors that influences clouds and precipitation. So what is the CORDEX-FPS-CPTP? The FPS stands for the flagship pilot study. Actually, there are 9 endorsed active CORDEX-FPS activities here. So in our CORDEX-FPS-CPTP, we mainly focus on the convection-permitting simulations over the Tibetan Plateau as well as its surroundings. with a particular focus on the mesoscale convective systems. And within our project, we have done several case studies as well as 1 year hindcast. And at current state, we have more than 3 sets of multi-year or saying decadal long simulations here. But within my talk, we will focus on the 1 year simulations, which is recognized as water year 2020. So why we focus on the year 2020? Because a lot of areas of the Eastern China as well as East Asia has experienced a record-breaking heavy rainfall, which is which we called violent Mayu storm over the summer of 2020. So the year 2020 Mayu season was characterized by an early onset and a late withdrawal, which resulted in an extended duration and abundant rainfall and a high frequency of extreme precipitation events. So to answer what is the current performances of the convection-permitting modeling over this extreme record-breaking summer, we use the GPM emerge datasets as well as the CMA multi-source precipitation analysis. And then we're focusing on the early summer season, which is June, July in the 2020. And we use the already present variables, combined shower sightings that includes area, intensity, and duration to define the MCS. And we use the iterative rational tracking method to identify and track the MCS among the observations as well as our kilometer scale convection-permitting simulations. So what is the added value when we use the rain cell tracking method? The right panel shows accumulated rainfall amount during a heavy rainfall event. So if we identify and track the heavy rainfall system, we could describe and store the fine scale features of the heavy rainfall system, which including the rainfall area, the precipitation intensity, as well as its moving speed and duration to store in the file. And we could compare our convection-permitting simulations versus the observations, and we could see how well our model availability is. So in terms of the convection-permitting simulations, we use at least 8 members of the kilometer scale simulations using WOLF, and one is the control run, which is also the reference run, and 4 members focusing on a single perturbations, focusing on the macrophysics, and 2 members focusing on the PBL scheme, and 1 member focusing on the double size the model integration domain. So let's delve into some results. So in observations, we have found is the MCS precipitation exhibit 3 major rainfall centers, and all these 3 rainfall centers are closely associated with the topography, which is the Dabie Mountain, and the secondary topography step, which is Wushan Mountain and Daba Mountain, and the northern side section of the Wuyi Mountains, which means all the 3 rainfall centers are closely with topography. And how well is our convection-permitting simulations? So overall, each member could reproduce the spatial pattern of the MCS precipitation patterns. However, substantial differences exist among different members. So if we zoom in to look at the different members focusing on the macrophysics, we could find that the members using WD6 and Whiting scheme underestimate the magnitude of the MCS precipitation. However, those members employing the WSM5 as well as the Morrison scheme showed better agreement with the CMPA graded observations. And in terms of the PBL scheme, compared with the MYN3 scheme, it has underestimated the magnitude of the MCS precipitation a lot. The members using the YSU scheme and Shihong scheme showed better agreement with the CMPA. And besides, we investigate which member is better and which member is not that good. And one interesting phenomenon, it should be noted that there are some, common bias across different kilometer scale simulations. What we have found is all the kilometer scale simulations by using Wolf exhibit a consistent bias characterized by a smaller precipitation coverage, but with a higher precipitation intensity. And this kind of bias is also evident in global kilometer scale simulations. So compare with the Himawari satellite retrievals and all the simulated kilometer scale simulations, the cloud and rain clusters appears more spatially fragmented, but more concentrated in intensity. And this kind of phenomenon we also shown in the WCRP global hexagon global convection-permitting simulations, which held earlier this year. And what if we have double the model integrating domain to its double size? What will the performances of the kilometer scale modeling will be better or not? So this figure shows the GPM and the CMP as well as our convection-permitting simulations, the results here. So what we have found is the GPM shows a continuous precipitation center over the eastern China, because we know that although the horizontal resolution of GPM is 10 kilometers, right, but the effective horizontal resolution of this kind of precipitation data set should be 30 to 50 kilometers. So it cannot well represent the small features of the MCS heavy rainfall. So on the contrast, our convection-permitting simulations achieved a better description of the total precipitation comparable to, and in some aspects, even that outperforms than that of GPM. So in terms of the MCS precipitation shown here, what we have found is compared with the GPM, the Wolf showed better agreement with the CMPA in terms of the both the peak intensity as well as the spatial pattern of the MCS precipitation. So here is my short summary of this preliminary results. So based on the first long-term multi-member kilometer scale ensemble simulations or the Tibetan Plateau as well as these downstreams, this study examined the intermodal differences as well as the common bias in simulating the MCS in the Super Meiyu in the year 2020. So what we have found is a consistent bias was found across different members, which is featured by a smaller precipitation coverage, but with a much higher precipitation intensity. And double the model integrated domain indeed improve the simulation in terms of both the total precipitation as well as the MCS precipitation. And compared to the GPM, our Wolf convection simulations at 4 kilometers was comparable to or even outperformed than that of GPM. I think that's all my talk. I'm happy to answer the comments or any questions. Thank you.
Very good. I'd like to invite some questions. Okay, Kristen.
Very nice talk. I had a question about your last point here. So the iMerge data is actually pretty well known to underestimate the intensity of precipitation. Have you considered looking at the actual radar data that occurred in 2020? It's about 5-kilometer grid spacing, just to see if the if the intensities are better matched to the 4-kilometer WRF simulations.
Yeah, that's a good question. So actually, our this kind of data, which is called CMPA, is combined precipitation analysis, which indeed also interpret with the radar data. So I have compared with those two products in simulating the precipitation intensity frequency fractures. So compare with this kind of data sets, the GPM indeed underestimate the heavy precipitation intensity, especially the intensity over 40 millimeters per hour. Yeah.
Thank you.
Andy?
Yeah, very nice results. I had 2 questions. Do you see the same biases in the double domain experiment where you see two small MCS systems that are too intense, or are these biases anyhow affected by the doubling of the domain?
Yeah, the short answer is yes. Yeah.
So they're the same biases or they're different?
Yeah, the spatial how to say, the spatial scale is smaller, but the intensity is also
this stays the same. Yeah.
a little bit stronger. Yeah.
And do you know why you get this improvement? Is it because you go farther south and you better capture the monsoon circulation, or did you look into that?
How to say? In my opinion, maybe it is related to the microphysics because we have already done two kinds of simulation using different microphysics.
No, I mean the doubling of the domain size.
Yeah. Two members. One is with Thomson scheme, the other is Morrison scheme, and there show some differences in simulating the precipitation intensity here. So we could discuss more in detail after. Yeah.
Thank you.
Thank you.
Okay. Any other question? Okay. Thank you. Then we will move into the last presentation by Yi-Chi Wang, future change in extreme precipitation events and their underlying processes across European regions.
Hello, everyone. I'm Yi-Chi Wang from Swedish Meteorology and Hydrological Institute. I realize that I'm the only thing that's standing between you and the banquet, so I will try to be concise and to the point. And this is actually a teamwork of with my colleague in SNHI and the collaborators in aspect projects, the EU project. And the title is broad, but it reflects our hope to develop an event-based framework that could apply to various extreme events over Europe. But today, I will mainly focus on the extreme rainfall events over the northern Italy, which is shown in the photos here. Okay. So I will start by introducing the event-based downscaling and its application to the northern Italy here. It's called Emilia-Romagna region. And it is a flood-prone region because especially when there is a Mediterranean cycle that is coming in with the right direction, which will have a huge moisture transport into the region. And because of the Apennines mountain here, it could have a huge, up to 200 millimeter per day over the region and have the floods like the Storm Minerva in 2023. And I will then present some preliminary results and the challenges of this study and close with a summary and outlook. Okay, so the core of our regional modeling system is Eddy. So both Ula and Laura has introduced it. So consistent with other models that we found that using the convection-permitting resolution to 3 kilometers can help to simulate the rainfall more realistically, like this case in Sweden in summer. So however, the CPM is very costly. So here we are exploring to use the event-based downscaling. So we're targeting only the key events while retaining the convection-permitting modeling resolution. Okay, so there are two stages of this event-based downscaling. So first, we need to detect the events from the coarser resolution data sets, usually from climate models or from the reanalysis, like ERA 5. And here, like we use the area average daily rainfall over the Emilia region, and then we identify events which shown as the gray bar here. And after we got the list of events, we actually use the downscaling framework with Eddy to downscale to 12 kilometers and to 3 kilometers to have a final rainfall features. Okay, so the domain setup is the two nested domain with the outer domain covering Europe and the inner domain centered on the Emilia-Romagna regions. And we test the storm Minerva case with ERA 5, and you can see that by downscaling to 3 kilometers can actually produce the better intensity and the position of the rainfall compared with the observations. And we especially choose the inner domain to initiate 1 day before the event to keep the circulation over this region better. Otherwise, you will have some shift of this rainfall locations. Okay, so we then do a composite for the 10 historical events, and compared with the observations, we think our downstream framework basically capture the region-wide precipitation and the measurement over the mountains, although it's kind of underestimate. And we have a better distribution for hourly rainfall over this region. Okay. And eventually, the goal of our project is to provide the climate change information of these extreme events. So we aim to provide a catalog of events and how they change in terms of intensity, duration, etc. So here we take advantage of our in-house SMHI large ensemble with 50 members based on EC Earth models. And we choose the period around 2000 to represent the scenario of 1 degree warming than the pre-industrial period to compare with the period around 2040 representing the 2 degree warming scenarios. So by comparing these two event statistics, we can have some information about how the future extreme event changes over these regions. So in order to do that, we need to simulate a lot of events. So we basically build out a pipeline which simulates the events. And we've studied some preliminary cases. So here I showed you some of the cases by simulating these historical events. As you can see that comparing with ERA 5, the EC Earth is 80 kilometer resolution, which is much closer. And the rainfall characteristic after downscaling can be pretty different, which will present a challenge later in the presentation. And we also do that for the warming scenario, 2 degree warming scenario, and you can see these are some cases which provide a pretty good simulation of these extreme events. Based on these preliminary results, we are actually identified the 2 challenges for event-based downscaling so far, and we are still working on it. The first one is the event detection is pretty important. So we found that by using the rain-only detection in EC Earth, it sometimes misalign with after downscaling, like this case, there's some rainfall over the region in EC Earth, but it's gone after downscaling. So we are thinking that we may need to refine the detection criteria with more information, such as the circulation to capture probably the cyclone, for example. And another challenge that we have is the soil moisture spin up. So this is the sensitivity test by initiate the events with dry and wet soil moisture. And you can see that for the precipitation, the rainfall changes is pretty random, but it's still some differences. It makes a huge impact when you try to simulate the air temperatures. So we are working on a good soil spin up scheme in order to fix this problem. Especially this region is highly irrigated. So how to incorporate the irrigation into the soil moisture to get a realistic bottom condition is really a challenge. Okay, so to summary, we've built up an event-based downscaling framework with convection-permitting modeling. And we found that it's pretty promising with reproducing this extreme rainfall event over Emilia-Romagna, although the event detection and soil initialization presents some challenges. And for the future, we are thinking to expand it to heat wave studies and maybe to urban and more regional contexts. And we also try to connect that with visualization to facilitate decision making for stakeholders and to compare with the climate long simulations such as CORDEX simulations. Okay, that's all for my talk. Thank you.
Thank you very much. Any question, comment? Okay, please go ahead.
Thank you very much for your talk. These events in Italy was particularly important since practically Emilia-Romagna, in just 2 weeks, was affected by 3 different floods associated with not very strong cyclone circulation, whatever. But did you expect, for example, that maybe some preconditioning may affect also the results of your detection? For example, pre-existing soil moisture content associated eventually with previous events can somehow influence your technique or whatever?
Yeah, this is a very good point. Yes, we from previous study and also from our study, we also find that the soil moisture itself matters in terms of the simulations. So that's why we think we really need to have a good soil moisture spin initialization.
In Italy there was also a huge discussion about attributing these events to climate change, because some people say it's not simply just one. This day was these events, I think, was 3 days continuously of rain. Produced by not a very strong cyclone. The sun was just stuck there and was able to produce a significant advection of moisture even from subtropical area. So probably you choose a very complex events, and I'm really interested in these results, and congratulations.
Yeah, thank you.
Okay.
Yeah, so currently we are using, so before running each event, we are actually offline spin up the soil moisture, but it also the other challenge comes in as like if there's some irrigation process which is not included in the models, you will get it wrong, like soil status in this case. So I think it's really tricky to carefully choose adjust the spin up. Yeah. Yeah, yeah, yeah. I'll be happy to.
Any other question, comment? Okay, Joy.
Thank you. No. So just initiate from the GCMs.
Yeah, I guess in the future you will do data simulation, both atmospheric variables and soil moisture, something like that.
Yeah, because we are doing it more from a climate perspective, so we're probably not doing much simulation. But we do consider to include things like irrigation into the model to facilitate the simulation.
Yeah, in doing that kind of thing, the response time scale is different for atmospheric variables and the soil moisture. So it makes some kind of headache when you couple the model and do the coupled data simulation. So,
yes.
Okay.
Yeah.
Any other question, comment? Good. Thank you.
Thank you.
And this concludes our last session. Thank you, everybody, to remain here to the end. And I think we have an announcement for our dinner, right? Conference dinner.
Yes. On behalf of the organizing committee, thank you all for your participation today. For those who are joining us with the conference dinner this evening, we will provide bus transportation outside. Please gather at the reception area, and our crew will pick you up to the bus transportation at 5:15. So 15 past 5, we will have crew to pick you up to the bus. And while waiting, we will take a picture in front of the backdrop. So please smile. And thanks again for being part of this journey today. Kindly ensure that you take all of your belongings with you and we look forward to seeing you tomorrow morning for the final day of the workshop. And we'll begin the registration tomorrow at 8:30 a.m. and the first session will start at 9 a.m. and have a wonderful evening. Thank you.